Today we're going to further discuss the concept of area with integrals. We found out that the integral gave us the area underneath the curve, but that's not exactly the entire story because there is a problem that comes up with looking at the area under a curve. Let's set up this problem by finding the area under f of x equals x squared minus 3x from x equals 1 to x equals 3. And we found out in yesterday's video that the area under the curve is simply the integral in that range from 1 to 3 of the function x squared minus 3x dx. And we can easily evaluate that. That's x cubed times 1/3 minus x squared times 3/2. And we're going to evaluate that from 1 to 3, which means we take 1/3 times 3 cubed minus 3/2 times 3 squared. And then we subtract 1/3 times, this time using the 1 cubed, minus 3/2 times the 1 squared. And so simplifying this a little bit, 3 cubed is 27. 27 divided by 3 is 9, minus 3 squared is 9, times 3 is 27/2. Distributing the negative through, so we're going to have a negative 1/3 plus 3/2. And when we do this on our calculator, 9 minus 27/2 minus 1/3 plus 3/2, we get negative 10/3. Well, wait a minute. The question was to find the area. How is the area negative? Well, this might help by looking at a picture of what's going on here. X squared minus 3x, if we were to factor that, it would be x times x minus 3. So we have a 0 at 0 and 3. The graph comes down and comes back up. And we were particularly interested in the area from 1 to 3. So we're particularly interested in this area to the right from 1 to 3. Well, here's the catch. Area is the area beneath the curve, but this curve is actually beneath the x-axis. And so what happens is we end up with negative area. And so how do we account for that? The solution we're going to do is we're going to say, how about this? Area can never be negative. Area has to always be positive because you can't take up negative space. And so the solution we're going to do is we're going to take the opposite also known as subtract of the part below the x-axis. So instead of doing the integral from 1 to 3 of x squared minus 3x dx, we're going to take the opposite of that and put a negative sign in front. So when we evaluate this, it's the same work, there's just a negative sign in front that's going to distribute. And so instead of getting negative 10/3 like we did before, it's going to be a positive 10/3. The area is 10/3 units. It's just below the x-axis, so we had to do the opposite of the integral. So that works. If we get a negative answer, just make it positive. Seems simple enough, right? Well, actually, that complicates things because now we have created another problem. Let's find the area f of x equals 4x cubed minus 24x squared plus 44x minus 24 from 1 to 3. Well, again, we could just take the integral, and our old philosophy was if it turns out negative, we'll just make it positive. So we're going from 1 to 3 of 4x cubed minus 24x squared plus 44x minus 24 dx. And so we have x to the 4th divided by 4 is 1, minus x cubed, 24 divided by 3 is 8, plus x squared, 44 divided by 2 is 22, minus 24x integrated from 1 to 3. And so we plug that in. We've got 3 to the 4th minus 8 times 3 to the 3rd plus 22 times 3 squared minus 24 times 3. And then we subtract, in parentheses, the whole thing, 1 to the 4th minus 8 times 1 cubed plus 22 times 1 minus 24 times 1. Cleaning it up a little bit, 3 to the 4th is 81, minus 3 cubed is 27. 27 times 8 is 216, plus 3 squared is 9. 9 times 22 is 198. 24 times 3 is 72. Minus, distribute the negative 1, distribute the negative plus 8, distribute the negative minus 22, distribute the negative plus 24. And so we do all of our math. 81 minus 216 plus 198 minus 72 minus 1 plus 8 minus 22 plus 24 is 0. The integral from 1 to 3 is 0. How is the area 0? We can't just make that negative because negative 0, that's just 0. Well, let's go back to our original problem. If we were to factor this original problem, probably would have to use the rational root theorem to get at it. But we would get 4 times x minus 1 times x minus 2 times x minus 3, which means this graph has intercepts at 1, 2, and 3. And because it's cubic, we know it comes in from the bottom, bends down, bends up, and goes out the top. And so what we're actually finding is the area from 1 to 3. So from 1 to 2 is all above, and from 2 to 3 is all below. You see, the problem is the areas are both the same on top and bottom. This one on the left is a positive area. The one on the right is a negative area. So what we're going to have to do is we're going to have to account for those different areas in different sections. The solution to this problem is going to be to only take the opposite of the negative parts. In other words, we are subtracting, which is the opposite, parts below the x-axis. So in other words, we've got this range here. When we take our integral, we're only going to do the integral from 1 to 2 of our function, which was 4x cubed minus 24x squared plus 44x minus 24 dx. And then we're going to subtract the negative part. The negative part was the integral from 2 to 3. Just taking the opposite of that negative part, so we end up with positive area from that 4, where do these extra spots come from? 4x cubed minus 24x squared plus 44x minus 24 dx. And that way, the left part will give us the positive, like we wanted, and the right part will make it positive by subtracting, like we want, and then we will have a total area between the x-axis and the curve, like we want. To help with this negative, these negatives get really ugly. I always distribute the negative through the integral. So I'm going to make that plus negative 4x, positive 24x squared, negative 44x, positive 24. Distribute that negative through so we don't have to worry about sign problems. And then we take the integral, and that's going to be x to the 4th divided by 4 is 1, minus x cubed, 24 divided by 3 is 8, plus x squared, 44 divided by 2 is 22, minus 24x integrated from 1 to 2, plus now we've got x to the 4th divided by 4 is negative 1, plus x cubed divided by 3 is 8, minus x squared divided by 2 is 22, plus 24x, and this is going to be integrated from 2 to 3. Now we just have to plug our values in. It's going to turn into a long addition subtraction problem. Fortunately, our calculator is going to help with the ugly part. We've got 2 to the 4th minus 8 times 2 cubed plus 22 times 2 squared minus 24 times 2. And then we subtract the whole thing in parentheses. 1 to the 4th minus 8 times 1 to the 3rd plus 22 times 1 squared minus 24 times 1. Close the parentheses. Then we plug 3 into the next part, so that's negative 3 to the 4th plus 8 times 3 to the 3rd minus 22 times 3 squared plus 24 times 3. And then we have to subtract. I'm running out of space, so going on to another line here. 8, oops, sorry, it starts at the negative x to the 4th, doesn't it? So negative 2 to the 4th plus 8 times 2 to the 3rd minus 22 times 2 squared plus 24 times 2. Close the parentheses, and let's clean it up. 2 to the 4th, that's 16. Minus 2 cubed is 8, which gives us 64. Plus 2 squared is 4 times 22 is 88. Minus 24 times 2 is 48. And when we distribute the negative, we get minus 1. Distribute the negative plus 8. Distribute the negative minus 22. Distribute the negative plus 24. Minus 3 to the 4th is 81. Plus 3 to the 3rd is 27. Times 8 is 216. Minus 9 times 22 is 198. Plus 24 times 3 is 72. And now when we distribute the negative, we get plus 2 to the 4th is 16. Distribute the negative, we get minus 2 cubed is 8 times 8 is 64. Distribute the negative, we get plus 4 times 22 is 88. Distribute the negative, we get minus 84. I'm sorry, 48. Said that backwards. And we get this long subtraction problem, but it's going to be our answer. 16 minus 64 plus 88 minus 48 minus 1 plus 8 minus 22 plus 24 minus 81 plus 216 minus 198 plus 72 plus 16 minus 64 plus 88 minus 48 equals a big 2. A lot of math for a 2. But now we know that the area under our curve, if you remember our picture up above, has a total area of 2. It seems that there is a 1 area in each little hump. And so 1 and 1 gives us a total area of 2 between 1 and 3. So there was a lot of arithmetic here because it just got really long with all the subtracting and adding. But it's just arithmetic, plugging in a number and solving. The process we go through to find an area is going to be, first we're going to sketch the graph and divide it into positive and negative regions. Once we do that, we can take several integrals, subtracting the negative regions. So for instance, if we are asked to find the area under f of x equals 9 minus x squared on the range from 0 to 6, we're first going to graph a picture of what this looks like. To help us with the zeros, we'll factor our function. That's 3 plus x, 3 minus x. That's a difference of squares, so we know x is equal to 3 and negative 3. Those are your x-intercepts. So 1, 2, 3, 1, 2, 3, 4, 5, 6. So negative 3 and 3 are the x-intercepts. It's a negative x squared, so it comes in from the bottom, goes out at the bottom. That's probably too steep. Let's we're gonna do this. So that's kind of parabolic, a little fat, but that's okay. And we want the area from 0 to 6. So here's 0, here's 6. We want the area enclosed by the x-axis. So this area to the right and this area to the left. And what you notice right away is that the left part is above the x-axis and is positive. The right part is below the x-axis. It is negative. So that means we're going to have the first integral positive, the second integral negative. So we're going to integrate from 0 to 3, and then from 3 to 6. So 0 to 3 of 9 minus x squared dx. And then we're going to subtract, because it's negative, the integral from 3 to 6 of our same function, 9 minus x squared dx. To avoid confusion, I like to distribute that negative now. So we'll make it negative 9 plus x squared. That way we don't have to worry about any issues later. Well, let's find the integral. The integral of 9 is 9x minus x squared becomes x cubed, 1/3. We're going to integrate that from 0 to 3. Plus, we've got a negative 9x plus x cubed divided by 3, 1/3. And that's going to be integrated from 3 to 6. It won't always split in half like this, but this one was nice. It did. So we've got 9 times 3 minus 1/3 times 3 cubed. And then we subtract 9 times 0 minus 1/3 times 0 cubed. Plus, we've got negative 9 times, the top limit now is 6, plus 1/3 times 6 cubed, minus the whole thing, 9 times 3, negative 9 times 3, don't lose that negative, plus 1/3 times 3 cubed. And now let's clean it up. 9 times 3 is 27, minus 3 cubed is 27 divided by 3 is 9. Distribute the negative, we get minus 0. Distribute the negative, we get plus 0. 9 times 6 is negative 54. Plus 6 cubed is 216. 216 divided by 3 is 72. Then we distribute the negative. Negative, negative makes it positive 27. Distribute the negative makes it negative 9. 3 cubed is 27 divided by 3. And then we just go to our calculator. We've got 27 minus 9, a couple zeros, minus 54, plus 72, plus 27, minus 9 is 54. Our total area for this curve is 54. All that orange stuff that we colored in has an area of 54. Probably not really to scale because it doesn't look like 54, but our graph didn't have to be to scale. We just had to find out where it was positive and negative. 54 is our total area. That process is going to be what we're going to use on every single problem here. So number 2, when we're asked to find the area under f of x equals 1 minus 1 over x from, we'll go e to the negative 1 to e to the positive 1. First, we're going to want to graph it. You'll notice that we are going to have a vertical asymptote at 0. Because if x is 0, it's undefined. You'll also notice that if we take the limit as x goes to infinity, the 1 over x goes to 0, and we have a horizontal asymptote at 1. And we could take the second derivative to look at the concavity. We can look at the first derivative to see where it's increasing or decreasing. Turns out that it is always increasing. So it's going to be increasing and increasing. What we're going to be particularly interested in is where does it cross the x-axis? Because that's when we're switching from positive to negative. Well, we can set this 1 minus 1 over x equal to 0. And if we add 1 over x to both sides, we get 1 equals 1 over x. Multiply both sides by x, and x equals 1. So at 1, that is our x-intercept. That's where our integration is going to have to break. E to the negative 1, that's really close to 0, not quite. So it's going to be around here. And regular e, that's 2.18, so that's going to be out here. So we want the lower area at first. and then it goes above up until we reach the point of e. So this is e to the negative 1, and this is e to the first. So we're going to need two integrals. The first integral goes from the lower limit of e to the negative 1, and it's going to stop at 1. And because it's below the x-axis, we're going to make it negative. 1 minus 1 over x dx. The next part is above the x-axis, so we make it positive, and we're going to integrate from that 1 to the e of 1 minus 1 over x dx. And again, I'm going to take care of this negative right away, change it to a plus, and make that a negative 1 plus 1 over x, so I don't have to worry about it later. Now we're ready to find that area. Antiderivative of negative 1 is negative x. The antiderivative of 1 over x is the natural log of x. And we're going to integrate that from e to the negative 1 to 1. Plus, the integral of 1 is x, minus 1 over x is the natural log of x, and we're going to integrate that from 1 to e. So, let's plug those values in. We've got negative, first plugging in 1, plus the natural log of 1, minus the entire thing, which is negative e to the negative 1, plus the natural log of e to the negative 1, plus, the next part we start at e, so it's going to be e, minus the natural log of e, minus the entire thing, plugging 1 in, 1 minus the natural log of 1. This is going to clean up nicely. We've got negative 1 plus the natural log of 1 is 0, because e to the 0 is 1. Distributing the negative, we have plus e to the negative 1. Distribute the negative, we got minus the natural log of e to the negative 1. Bring that exponent out front, and we get a negative 1. So a negative negative makes it a positive. Plus e minus the natural log of e, which is 1. Distribute the negative, minus 1. Distribute the negative. Negative times a negative is a positive, and the natural log of 1 is 0. Combining like terms, we got negative 1 plus 1 is 0. The zeros we don't really care about, so there's a negative 2 total. There's a positive e, and there's also an e to the negative 1, which is 1 over e. And that is going to be our area. We could type it into our calculator, negative 2 plus, and then if we hit second ln, we get the e. You probably need to tell your calculator that's a first power, plus 1 over second e to the first power. And that gives us approximately 1.086. If you prefer the decimal, is going to be the total area. The left part was negative, the right part was positive, but when we made those adjustments, we got our actual area that was shaded of negative 2 plus e plus 1 over e. I want to notice how these problems are different than the ones we were solving before. Yesterday, we were just interested in the definite integral. Plug the values in, subtract the upper and lower limits, and you got your solution. That was the integral. If the question specifically says, find the area, that's the difference today. We need to be careful of those negative areas. And so our process is going to be, we'll have to sketch a graph and divide it into positive and negative regions. Then we will take several integrals, however many are necessary. We always did 2 in this video, but sometimes you need 3, 4, or more. And we will subtract the negative regions. That's the big new idea for today. Sketch the graph so we know where it's positive and negative, and subtract the negative regions. Take a look at the homework, try a few of these, and we will see you in class tomorrow for some area problems.